You can now begin. Thank you.
Okay, so very welcome to our short presentation about our pressure cell portfolio from Anton Paar. Um, quick, just words to myself. My name is Markus Nemeth. I'm from Anton Pars, located in Germany, and I'm working with the company for the past 12 years now and doing such seminars and training and installations all around the world, and gained over the time a little bit of experience with rheological applications. And so I'm happy to go through this presentation together with you. Um, Today, I would like to invite you as well. If you have any questions, please feel free to ask Mohammed. Maybe you could manage that. If someone has a question, write it in the chat. That would be the easiest way, and we will have a Q&A session at the end. I guess it will be not a problem if you ask in Arabic, and Mohammed will be happy to translate. So don't be afraid, feel free to ask. And if I'm speaking too fast or if my German accent is too terrible, please as well let me know, and I will explain in a different way. Good. So as we said, um, I'm working for Anton Paar. So we are a manufacturer for analytical instruments for different applications and ranges. And I guess as this is not the only session, you have seen already some other applications. Um, Today we will focus on rheometry and rheology. So we are looking on the measurements on a rheometer. That is an instrument which tests usually the flow or deformation behavior of any kind of sample. So we can measure viscosities, we can measure viscoelastic properties, and of different type of samples from liquid to solid. Anything is in there. We can as well vary the temperature in a wide range. What you see here is a wide range of different types of our cells we can add to the rheometer. So we have a wide opportunity and a wide range of different accessories which can be added to the rheometer. So for example, you could add a microscope with and check for the crystallization behavior of a crude oil, which is treated with different pour point depressants. You could measure the influence of these pour point depressions onto the viscoelastic properties to say, okay, is it pumpable at different temperatures? Um, uh, so as you see, we have a wide range available. Today, we will focus on the pressure cells, so we can apply pressure to
Sorry, Markus.
a sample. Yes, please.
I think you have the wrong screen. Is it possible?
I'm not sure. I just share my PowerPoint presentation.
I don't know. I only see the first slide
Okay.
or something. It does not work for me. I don't know if what the others see, but I only see the first slide.
Which is the first slide in your
Product
case?
presentation, pressure
Okay.
cells.
So you don't see that it's now switching the pages.
No.
Okay, let's quick change that to full screen. So let's do it like that. That should be better.
Yes.
Good. Okay. So so in the center you see our rheometer. We have a wide range of different types of applications possible. As we said, from liquid to solid, we can measure powders. We can measure as well in the rheometer friction, for example. If you want to know how the your oil reduces or how the drilling fluid reduces friction internally to increase pumping, or if you have different um, drilling core materials, how that is influenced by the drilling fluid, for example. Stuff like that can be tested. Today, as we said, we focus on the pressure dependency of our samples. So just a quick overview. We have two different types of pressure cells. So we will have an overview over there, the rheological influence, and then we focus on our two systems. We have one type of pressure cells, which is a gas-filled headspace. So there the pressure is applied by gas, compressed gas. And the second option would be a liquid-filled pressure cell where we have the pressurization by a compressed liquid, and there we can go to higher pressures for sure. So our two options we have, on the one hand, on the top, we see our gas-filled headspace pressure cells. So the principle is the magnet coupling here on top is connected to the rheometer. To have a complete closed system, we have here our pressure cell. So we have the sample, we have a bulb, and this is connected to, in the pressure head, to a magnet, which is connected to two bearings. And then if the outer magnet field rotates, the inner follows. So that's the principle. The same applies for the liquid-filled pressure head and pressure cell. But there, the magnetic part is the bulb. So one thing is important for sure, samples with magnetizable particles might be hard to not measurable at all. So that's a very important thing. We measure usually with the 150 bar or the 400 bar pressure cell, where we can go in a wider range from temperatures up to 300 degree would be possible, down to -30 or -10. Whilst the liquid-filled ones can go only from ambient to around 300 degree. Yeah. Benefit, for example, of the 170 bar pressure cell is that we can pressurize it here, liquid or gas pressurized. Well, this is something we will see later. So two different principles of pressurization. And so what is the influence on of the pressure on rheology? So in general, you would say, pressure, liquid is incompressible. It's not 100%, so we can apply pressure. The molecules are forced to get closer to each other. And what we see then is an increasing rheological behavior, so an increasing viscosity usually. You can see that in the graph on the bottom right. With increasing pressure, we see the same sample responses with higher viscosities. The reason is, I hope you know that the viscosity eta in Pascal seconds is the, that's the viscosity. So when we see this eta sign, that's the viscosity of our sample. Viscosity can be described as the internal friction. So if you move something, molecules, particles, whatever is in our sample needs to pass alongside each other. So for sure, if we have more molecules in a smaller space, we have a higher inner friction, which leads to an increasing viscosity or rheological behavior. So dissolved gases, on the other hand, can act as a plasticizer, so as well change the rheological behavior. You could see how the influence of CO2, for example, in the sample acts, how much CO2 is dissolving, is the sample flowing easier or less easy? Stuff like that can be tested with a pressure cell quite easily. Yeah, so you can check for high pressure injection. You can simulate pumping processes under pressure. On the other hand, for sure, if you have your sample from an oil well or whatever under pressure, taken as a sample in 1,000 meters depth, you can as well put the sample directly with some effort into the cell and you can prevent evaporation and degassing of the sample and see the influence of possibly of that dissolved gases in the sample. As well, diffusion speed of gases and hydrate formation can be measured. For sure, the classical applications like drilling fluids, so more or less polymer solutions, the influence of different amounts or concentrations of polymer solutions in a sample, in a drilling fluid, for example, or in a fracturing fluid can be measured as well. So let's start with this gas-filled headspace pressure cells. So this is a picture of our 150 bar pressure cell. You see on the right-hand side that that line is the gas pressure connection, and on the front we have a temperature probe. On the back is a safety valve, and here on the left-hand side we could add sample to the pressure cell. So you could connect a sample under pressure and force it with a pump or whatever into the pressure cell against an outside pressure. So you have your sample gas filled and evaporation tide transferred into the cell, for example. So that would be a possibility as well. So typical applications, drilling fluids, fracturing fluids, the crude oil itself, polymer melts for the petrochemical industry. Food is as well something what you could check for, but for sure not today's main focus. So a real measurement, how does the viscosity react to a pressure increase? So we see we have ambient pressures, that's the black line here at 1 bar. That's the black dots is the viscosity. So we have here a viscosity in millipascal seconds of around 10, 20, let's say 25 millipascal seconds. And an increase of the pressure to 10 bar is showing a slight increase of the viscosity, and then going to 50, 100, and 150 bar leads to an increasing viscosity here. So we have a value change from, let's say, 25 to 29 millipascal seconds, which can be significant. In this case, it is significant. In other cases, it might be stronger or less strong. So that is a typical measurement of this was now a vegetable oil, just as an example, but most of the other oils behave similar. Oh, sorry, wrong direction. Now, here we have a used, in that case, a motor oil, so an engine oil, which was treated for a certain period of times and in a motor to check how the engine works. So as well here we are in the oil field, so past real petroleum behavior. And there you see we have an increasing viscosity as well due to increasing pressures. And from ambient conditions, we go to 30 bar, 60 and 95. And here we have a stronger reaction. We have here an increase from 390 millipascal seconds to 520 millipascal seconds. And for sure, if the viscosity is higher at higher pressure, so usually if an engine runs, you want to have a lower viscosity, which comes by the increased temperature. But as well, the pressure increase has a significant influence later on to the performance of an engine, for example. So that could be as well on site, on the drilling side, how the engines behave there. Or you can, how you pump the sample out. If you have your oil in a well which needs to be pumped, and you increase the pressure and you pump it stronger, and all of a sudden it's getting less and less sample out, so due to the increasing viscosity there. Here we have the same sample measured at negative 15 degrees. So as well, we can see here the influence of crystallization. So that sample started to show a crystallization of the particles which are there as The reason for these particles was wear in the engine. And there we see that we have here a shear thinning behavior, and we are in the Pascal second range now. So that oil is maybe not anymore very useful at low temperatures. Right. So about precision, you see here, there is a comment we have. Sorry, yes, please.
Please, what's the M? What's the meaning of M?
Oh, yes, I come to that point. That's the torque. So the torque is, let's say, if we have a rheometer, we rotate our system, right? So something is moving, and if you have a rotation, then the force we apply to the sample is not anymore a force, which is one direction. If you have a rotating system, we have a torque, and M is the sign for the torque. And here you see the unit, it's millinewton meter. And there we come to this point, what I was to explain now. The lowest torque range, if we average over a full revolution at one single speed or shear rate, which is equivalent to the speed, then we can go down to around 80 to 100 micronewton meter. And that low range is above the minimum range of a regular rheometer. And the reason for that is that we have this magnet coupling and ball bearings in the pressure cell itself. So the sensitivity of the instrument is not anymore as good because due to these ball bearings in the pressure cell. Right. And therefore, it's usually as well that we don't measure below or at very low shear rates in the pressure cell, just as a side comment. Good. Here we have a polymer solution, which is usually used in a drilling fluid as an additive. And there you see, for example, we have standard pressure cell, our 150 bar pressure cell, and here we do a temperature sweep. Yeah, so we go from 140 to 260 degree. And so we have a polymer solution at 40 bar, and we have, for example, compared to that, polystyrol at 40 bar as well. And there you see the temperature dependency under pressure of these polymers. Benefit is we can measure those samples even at elevated temperatures without having evaporation, or if you have a waterborne polymer solution, you can even go to higher temperatures and water is not boiling for sure. So the benefit here is to reduce the influence of the temperature, and on the other hand, to see how the sample behaves at different temperatures under pressure. We have a nice curve of a crude oil later on as well. Yeah, so this is a typical application as well to see how the temperature changes. Do we see possibly a certain temperature where my sample changes its viscosity quite dramatically, or how is the viscosity reduced? How strong is it reduced? You see the polymer solution has a steeper slope. So at 140 degree, we have doubled the viscosity. At 260 degree, the difference is far smaller. All right. Another idea here, we have another polymer solution, and the test was to measure at different pressures and at different temperatures. So here is the shear rate ramp. So we see we measure very low viscous samples. Therefore, we have high shear rates. At ambient conditions, that means ambient temperature, room temperature, and 1 bar, we have a viscosity shear thinning behavior from 5 to 4 millipascal seconds around. If you increase the temperature and increase the pressure up to 110 bar and 50 degrees C, we still see a drop of the viscosity. What does that mean? Very important. in rheology, temperature increase means always, except of a reactive system, always a drop of the viscosity. So higher temperatures, lower viscosities, right? What we learned so far is higher pressures, higher viscosity due to an increased inner friction. If you put both together, what you see is that the temperature has the stronger influence on the viscosity than the pressure, right? So pressure is as well important, but the temperature is stronger. In that case, you see here a drop of the viscosity. If we increase the temperature further, we drop even further down. If we reduce the pressure, you see we have just a small change in the viscosity, right? Higher pressure means higher viscosity, but here we can measure around 1 millipascal second. So you can see the influence, and this is quite nice, the influence of temperature and pressure, and you can vary both variables to find your optimum flow behavior of the sample. Here, very interesting is the measurement of solvents that could be of interest at different pressures as well. So here we've measured isopropanol, acetone, and pentane at different temperatures. And you see, on the one hand, this is again on the right-hand side is the torque. This is these light lines with no markers is the torque. And so here's our torque limit for this application. Therefore, we get not the perfect results, but still measurable results. And you see, we can measure down to a millipascal second or below with under very good conditions. And we can measure, here you see isopropanol, for example, at 78 degree, where it's usually already boiling. All right. Yeah, low temperatures can be measured, high temperatures can be measured. We can check for different application states. You can apply different shear rates to simulate pumping, mixing processes, the influence of additives to the sample. What else? Here, for example, that's a hydrate check. So we measure at 2 degree and just 8 bar over time. And so the pressure is here going down a little bit due to cooling. And there you see a drop of the pressure as we get a hydrate formation. Yeah. So here we act as well. We can check for hydrate formation at constant shear rates on the different concentrations as well can be checked for different temperatures, pressures, and the shear rates. Down here, you see this is the so-called Taylor limit, where the sample gets into a turbulent state from a laminar flow behavior. So as well, that can be checked. Hydrates, I guess that's more for the drilling behavior in Norway or something like this, but as well, it could be of interest for you. All right. Yeah. So this would be the applications of the typical gas-filled pressures up to 400 bar. You see the different pressure cells here, wide range. The 150 bar pressure cell, the small one, can go to the lowest temperatures like -30. And due to the small geometry in there, so we have a double gap geometry, but the lowest viscosity is around 5 millipascal seconds. Benefit here, it can be made out of Hastelloy, so that could be quite chemically stable. The other one for lower viscous samples and the higher pressures like 400 bars is made out of titanium, so as well we can check for that. Good. Yeah, so we have different options, and how does it look like? So again, here's a picture. Pressures applied with a gas from the outside. Yeah, so here we have the pressurized gas coming in. As well, the head space is filled. The torque is transduced with a strong outer and inner magnet, and the ball bearings hold the center shaft in let's say, in position, so that as well this bob is not swinging left to right and has low friction. So different types of geometries can be measured, used for sure. Very important is the temperature is mainly down here. So if your sample starts to evaporate, and it might up here have a little bit of lower temperature, so you might have condensation of, if in case if you use waterborne samples or you have an emulsion or something like that, after a measurement, this would be beneficial to wipe out quickly, right? So we pressurize the sample here up to 150 bar. We use usually gas pressure only. So we have this gas inlet of the large one. We have a PT100 connector because this is massive metal. That means we take the temperature closer from the sample, and a rupture disc as a safety thing. Gas pressure cells can be used, as I said already, here with a pressure gas bottle that however you get the pressure there. So this is not included in the delivery. What we deliver is a so-called pressure supply unit with an inlet and an outlet, and then with the inlet there's a manometer, and you can add a pressure sensor to the side where we pressurize the whole system. Which gas you use is up to you. Yeah, so you can use CO2. We have customers using, or standard wise is nitrogen. You can use as well argon. We have customers using different types of materials. Important is now for this application that the maximum applicable pressure in this setup is the pressure of the gas cylinder. If you want to reach higher pressures, like the 400 bar pressure cell, there would be a necessity to build in between the gas cylinder a syringe pump, for example. So with two valves. So you pre-pressurize with the pressure cylinder with the gas pressure, close the valve and increase the pressure with the syringe pump, for example. Again, that's not included in our portfolio, so that needs to be handled from yourself, or we might have ideas how to solve it. Good. Yeah. So as we said, standard is the regular concentric cylinder. If you want to measure a little bit more precise at lower viscosities, we would measure with a so-called double gap geometry. If you have larger particles, or if you want to know the mixing behavior, you can have a stirrer in different shapes and whatever. So if you have, for example, a suspension with particles which tend to settle, you could have a stirrer in a certain shape that it prevents the particles from settling down. On the other hand, maybe not so often used in the crude oil or in the EOR applications, we can as well use parallel plates to measure, for example, polymer melts under pressure. But I have no example here because I guess this is not so much interesting. All right. From the gas pressurized systems to the liquid ones. So what is the difference? The difference is for sure as we apply pressure to the sample, we pressurize not anymore a gas, but we pressurize the entire liquid. What's the benefit? The main benefit is we can reach higher pressures. So here, for example, up to 1000 bar pressure can be applied. Here we have measured a vegetable oil just as an idea. And each of these points is a measurement at different pressures. So we vary it manually, the pressure. And you see, we can go from ambient to 1000 bar without any problem. Yeah? And the viscosity increase here is linear. Now that would be more interesting. Here we've measured a crude oil at 50 degree at different pressures. And what you see is up to a pressure of around 600 bar, which is already quite high, we have a linear increase of the viscosity. So like with the vegetable oil. So there is no big deal. As we said already, yeah, increasing the viscosity leads to an increasing pressure leads to an increasing viscosity, but at around 700 bar, something changes and we have a significant slope change. And that is a very interesting point, because this point can be, yeah, say something about your application. How does the sample behave down there? Most of the time, people assume, oh, an oil is just linear, increasing the viscosity with an increasing pressure. But this is not always the case. So something else happens in the sample, right, under these pressures, and we have an increased viscosity by, in that case, more than 100%. So from 70 millipascal seconds to above 150 millipascal seconds. Right. Yeah. The same thing can be done, but now to see the shear rate dependency, if my sample changes its viscosity at different shear rates, an oil we would assume does not change its viscosity depending on the shear rate. And so we measured here at different pressures. So normal pressure is the blue curve, our reference measurement with a CC27. So this is standard cylinder, showed almost the same viscosity values, which is okay. And then increasing the viscosity, the pressure by 250 bar steps leads to an increasing viscosity as well. But you see the distance between each run gets bigger and bigger and bigger. So as well, here we don't have a linear increase of the viscosity, but we have a curve-like function depending on the pressure. So as well, that could be tested at very high pressures.
Hello, Marcus. Sorry, it seems it has a problem with Marcus. So let's wait a little bit.
Is it now better?
Yes.
Okay. It seems that something kicked me out. So where did you lose me? Have you seen that slide already?
Yes.
Yes. Okay. Good. So we have the rod climbing effect prevented by the complete enclosed geometry and cell. And so we can measure that. As well, you see here over time at a constant shear rate of, here we measured at 170 reciprocal seconds. So we measured at a quite high speed, where in an open system, we usually see the influence of the rod climbing effect. There is no rod climbing effect as we have a constant viscosity. And in that case, this is quite beneficial, especially for fracturing fluids. Measured here at ambient conditions, 25 degree and 1 bar. That's the full part. You see the increase of the pressure to 150 bar does not have an influence on the viscosity. Whilst if you increase the temperature to 90 degree, there is as well no significant influence of the pressure to the sample, which is beneficial for sure if you want to if you have your fracturing fluid, you want to have it at the same pressure or at higher pressures as well, working as it should, yeah, as a fracturing fluid. What else we can do is check at constant shear rates again in rotation to measure the viscosity and vary the temperature. So here we've measured from 30 up to 120 degree in 2 runs. And you see, for example, what you can check is, on the one hand, against an open system, we prevent the evaporation effects of this water-based system on the one hand. On the other hand, we can check for temperature degradation, and so we can determine optimum working conditions. Yeah. So how long, this is over time for sure, how long can it stay at a certain temperature can be tested in another run as well. Yeah. So you see increasing temperature leads to, for sure, decreasing viscosities, but let's say from a temperature of around 80 degree, we have a significant stronger drop of the viscosity, which is not coming only from water evaporating or boiling or something like this. So something happens as well to the polymer in the sample. Right. What else we can check is, for example, crystallization of a brine fluid at different pressures. So you see here over the temperature at ambient pressure here at 700 bar and at 950 bar pressure of this brine fluid. And you see the higher the pressure, the lower the temperature where we have here the crystallization. So that dropping point down here is kind of sample is solid, and we've kind of lost the contact. We broke the sample, and the stirrer or the geometry, the meshing geometry is just sliding on the solid surface of the sample. But there you see at ambient conditions, we found a temperature of minus 17.5, and increasing the pressure leads to a lower crystallization temperature, for example. So different things can be tested. Mixtures in the sample. And so how is the working principle? You see, the lowest torque here is just around 400 micronewton meter, depending as well on the lubrication properties, as we have now here up on the bottom of the bob and on the top of the pressure of the bob, we have a so-called sapphire bearing, which has, as the sample is there as well directly present and the sample lubricates it, it has an influence on the precision of the sample. So around 10 to 50 millipascal second is the lowest viscosities measurable in the high pressure cells, for example. Principle, we have, it always looks like so big, but this is for sure just a drawing. So the principle is really like, we have here our measuring geometry, and we have up here the magnet around the outer magnet, and then in this very narrow gap, it's around 1 millimeter or less, we have our sample inside. Sample below, sample above is as well present for sure. And the 170 bar pressure cell has an input from the side, so we can have here liquid sample in, or we can pressurize it with gas, and that is as well quite beneficial. So you have different options there. Yeah. So we can use gas pressure or we can connect it. So this is the pressurizing system and the cell, and we have a manometer there and a search tank. So if sample would come out, it would not go into your piston or something like this. It would go first into the search tank to avoid sample getting out of there. Due to the design, it's available up to 170 bar and up to 200 degree. And as we said, we can, and this is the benefit here, as well have use it as a flow through cell, let's say. Flow through, that means we have a different bottom part and you can have a liquid pump or you pressurized sample in a gas cylinder or liquid cylinder under pressure, and you can, let's say, let the sample flow through. Here's a valve or whatever, and then you have a pump left and right and pump the sample in and out and in and out. Whilst the other option we described already, we have here our gas pressurization and with the search tank where overflowing sample can get in. The 1000 bar pressure cell works in a similar way, just that we have always the filling from the bottom and it's kind of overfilling on top. It goes out and then the filling part is removed. We have the magnet coupling on top and we have the magnet in the geometry and it's rotating inside there. Again, very quite good possibility to measure up to 1000 bar, and as it is made out of titanium, it is resistant against most of aggressive samples. Benefit as well, it can go up to 300 degree. If you would like to have a flow through option, that is as well possible. In that case, the maximum pressure is reduced to 400 bar. So how does it look like? You see we have different geometries. For the cup is always the same, so we have a small geometry for higher viscous samples or samples with particles in, but we as well have the option of very small gaps to reach higher shear rates, for example. Yeah. All of that is set together in the rheometer, and then we have here a pressurizing pump to increase the pressure in the sample. As I said, we can have the flow-through option, but then the maximum pressure is reduced to 450 bar. All right. Two options to increase pressure or fill the sample actually into the 1000 bar pressure cell or the 170 bar one is you can have the sample here on the side. It's sucked in by this hand pump. And if you close the hand pump, you can increase the pressure manually to 1000 bar. That's suitable for Newtonian or slightly viscoelastic fluids. So typically for your field, that would be the pure crude oil or let's say polymer solutions, which are used as a drilling fluid, whilst we have another option with a separator where we can as well have highly viscoelastic samples the um, in the system, as we have here a so-called separator, which is pressurized with a hydraulic pumping slope, and in here is a piston pressing the sample into the rheometer, and you can measure in there. Yeah. So even, and that's the cool part, even a fracturing fluid, which is extremely highly viscoelastic and absolutely not pumpable with a standard pump, can be applied here into the rheometer, even under pressure. So that would be as well modifiable. All right, just some overview. So benefits of the pressure cell. So you can have a wide temperature and pressure range up to 300 degree and 1000 bar can be measured. We can check for flow through or low temperature options. Yeah, so how does my sample behave if you have it pre-pressurized? You don't want to have it degassed before the application. So that is an option. You can have plate geometries. Hastelloy is available for highly corrosive samples. And for sure, if you have some special needs which are not fulfilled by our standard solutions, we have always customized solutions ready or help you with that. Yeah, you can check how is the pressure influencing the rheological behavior. We can prevent the evaporation of volatile materials. It should not be flammable though, for sure. Yeah, this whole parts are not X-proof, so not flammable. You can simulate your process conditions, different pressures, temperatures, speeds, mixing. You can check for mixing. You can check for, you could even mix and react your fracturing fluid within the pressure cell. So you can add different components to your sample under pressure and see how they react under pressure. Yeah, as we said, drilling fluids or fracturing fluids can be measured and pumped into the pressure cell. All right. So a bit quicker than expected. Now I'm happy to have some literature and have some questions answered from my side, if there are questions.
Thank you very much, Marcus, for this interesting session. Thank you all for attending. Please, if you have any questions, you can type on chat or raise your hand and talk. So we are now receiving your questions regarding the session. And if there are no questions, we will go on to the competition. So, no questions? All right. So
Good.
thank you so much, Marcus, for your time and effort.
You're
And
welcome.
we are now going to the competition. I will send in the link, so you can end the session anytime you want. Because we will continue with another lecture later after the competition. Thank you so
Okay.
much.
All right. Then have a nice day.
Thank you. You too.
And thanks for your time and all of you. If you have any questions, please get back to Mohammed and he will be happy to answer or transfer uh, knowledge, or we can interact through him as well. All right. Thank you very
All right.
much.
You're welcome. Thank you. شكرا لكم جميعا. دلوقتي احنا ان شاء الله هنبتدي المسابقة بتاعتنا. يعني طريقة المسابقة هتكون ازاي؟ انا هعمل كوبي وبيست لللينك بتاع السؤالين في الشات دلوقتي. الموضوع هيعتمد على السرعة. هما سؤالين يعني بسيطين جدا. هتضغطوا على اللينك اللي هبعته على الشات دلوقتي وهتجاوبوا على السؤالين. طبعا بعد كتابة الاسم والإيميل بطريقة صحيحة. وأول حد هيجاوب على السؤالين صح إن شاء الله هو هيكون الفائز. فاستعدوا بقى، افتحوا الشات بوكس دلوقتي. مستعدين؟ تمام، أنا حطيت اللينك دلوقتي، ودلوقتي تقدروا تدوسوا على اللينك وتجاوبوا السؤالين إن شاء الله. طبعا كل واحد ليه محاولة واحدة فقط للإجابة، فيا ريت نفكر كويس قبل ما نجاوب. الرابط بيعمل، يعني الناس عمالة تجاوب، فأكيد في مشكلة عند حضرتك في الإنترنت. تمام. خلاص احنا خدنا إجابة صحيحة. أستاذة أحلام بن حامد. خلاص كده المسابقة انتهت. أول إجابة صحيحة عندنا. أنا هعمل شير سكرين. شايفين عندي الشاشة؟ الشاشة واضحة عندي؟ حد سمعني؟
ايوه واضحه الشاشه.
يس واضحة. يس كلير.
تمام تمام. ألف مبروك. أستاذة أحلام بن حامد هي أول حد يجاوب الإجابة الصحيحة، وهي الإجابة الصحيحة لحد دلوقتي. إحنا نقدر نقيس الريولوجي لكل أنواع العينات، حتى العينات الصلبة. والشير ستريس هو directly proportional to rate of shear. فألف مبروك، وإن شاء الله هننسق إزاي بنقدر نوصل لحضرتك الكتاب.
شكرا شكرا جزيلا.
عفوا عفوا،
وشكرا
وأنا
على
بشكركم.
مساعيكم، وكل محاضرات
ألف
كانت
شكر.
جدا ملهمة وجدا انفورماتيف. ونشكركم نيابة عني ونيابة عن معنا الليبي وكل الليبيين اللي كانوا في المحاضرات. شكرا جزيلا.
احنا اللي بنشكر حضراتكم جميعا، واحنا لسه ما خلصناش. ان شاء الله هنكمل في محاضرة اخرى مع دكتور احمد نوح. ودي الحقيقة هتكون محاضرة مهمة جدا، لان بناء على طلبكم هو هيتكلم عن تطبيقات النانو تكنولوجي واحدث الابحاث اللي عملوها في معهد بحوث البترول المصري في مجال الدريلينج فلويدز. وهم الحقيقة واخدين الريوميتر بتاع انتون بار. فدي هتكون فرصة كويسة ان احنا نتعرض لبعض التوبكس المهمة. وطبعا يعني احنا استمتعنا بالمحاضرة اللي فاتت بتاعة الفورميشن دامج من دكتور احمد، فان شاء الله يمتعنا برضو بالمحاضرة بتاعة اليوم. وانا بشكركم جدا جدا على حضوركم المستمر لحد دلوقتي. وان شاء الله دي اخر محاضرة معانا نستمع اليها مع دكتور احمد ان شاء الله. ومش هطول عليكم في الكلام، اسيبكم مع دكتور احمد. ازيك يا دكتور احمد؟ ايه الاخبار؟
الحمد لله هندسة. بس السلام عليكم ورحمة الله وبركاته. صباح الخير عليكم جميعا.
عليكم السلام.
بس هي المشكلة ان هم اكسبايرد دلوقتي، لانهم واخدين محاضرة ساعة ونص قبليها. فانا بس
الحقيقه الصوت مش، الصوت
كويس
بيقطع شويه بس يا
علشان
دكتور احمد.
يقدروا يعملوا. بقول لحضرتك لازم يبقى فيه وقت كافي ليهم عشان يعملوا ريفرشمنت ما بين المحاضرتين.
بالظبط بالظبط. خلاص احنا ممكن نعمل ريست 5 دقايق.
فدلوقتي يعني حتى في الجامعه الامريكيه بيعملوا المحاضره مدتها ساعه.
تمام. امال انا كنت باخد محاضره 4 ساعات ليه يا دكتور في جامعه اسكندريه؟
غلط غلط، ما بتستوعبش كله.
والله ولا بستوعب اي حاجه. كنا بنطلع ننام.
لا، ما هو ده عشان كده انا بقول لك المحاضره مهمه ولازم يكونوا يعني انا كنت اتمنى انها تبقى الاولانيه عشان يبقوا فريش كده. يعني دلوقتي هم اكسبايرد، يعني لازم يكونوا واخدين وقت كافي عشان يقدروا يعملوا ريفريشمنت اللي جاي.
بالظبط بالظبط، بس لازم يكون ختامه مسك يا دكتور، فلازم نختم بمحاضره
ان
حضرتك
شاء
طبعا.
الله باذن الله.
ان شاء الله.
لا،
فخلاص
هيتبسطوا
يعني
جدا وان شاء الله زي ما انت قلت كده.
بالظبط. ان شاء الله. خلاص دلوقتي الساعه 3 الساعه 12 و3 دقائق، ان شاء الله 12
دقايق بعد
و10
اذنك.
ممكن نكمل.
اوكي، ماشي.
تمام، شكرا.